So the first thing I want to do with every problem is check if the energy is conserved in the problem. What does that mean? It means that all of your forces are conservative forces. And if all of your forces are conservative forces, what that means is you can solve your problem, solve your exercise, the way that we solved the last exercise, by finding the initial force, finding the final force, and setting them equal. I want to take an opportunity to talk about a common mistake as well here. Some people think that if you have conservative forces, it means you only have internal forces and no external forces. That is not true. That is absolutely untrue, and it will get you in a lot of trouble with some of these exercises. External forces are not related necessarily to the preservation of energy. They're related to momentum. And in fact, you can have external forces that are conservative forces that do preserve energy. Well, some of them don't, some of them still do. So a conservative force does not mean an absence of external forces. This similar mistake can be made in the opposite way. You can also have internal forces that are not conservative forces. So this is not a good measure by which to judge if you have a problem with preservation of energy. So let's return to our method. We need to check if we have conservative forces. The easiest way to check if we have conservative forces is to see if a given force has potential energy. A couple examples here above are the potential energy of gravity, UG, something can fall, or the potential energy that's elastic potential energy, that of a spring, because a spring can always spring back. If you have that potential energy in it, your energy is inherently a conservative force. Now, there are two other ways that I can check if I have a conservative force. The first is the rotor. We talked about that earlier, so I'm not going to get into that too much here. The second is if we have a force whose net work done is 0, then it is also a conservative force. That means that in going from point A to point B, if the work done equals 0, then you have a conservative force. Let's assume for a second that we have a problem that has conservation of energy. We've checked all of our forces and they're all conservative forces. Let's say for this example we're using the force of gravity and the force of a spring. We can then check the box that says that we have conservation of energy because we're dealing with only potential energies in this case, and move on to our next step. Now our next step is we can set our energies equal to each other. What do I mean by that? We can look at our final moment and our initial moment in the particular time we're looking at and set them equal. So our initial moment, the beginning of the problem, is EI, initial energy. And our last moment is final energy, EF. So we know that when we're trying to find the value of the initial energy, we can set it equal to the kinetic energy plus the potential energies. That's 1/2 mv squared plus whatever the potential energies might be in a given problem. Then I can take my final energy, EF, and again I set that equal to the kinetic energy, 1/2 of mv squared, plus whatever our potential energy may be at that moment. Again, it depends on the problem. Now when I say I'm setting the two equal, it literally means that I take an equation where EI equals EF. And this is the beauty with energy, is we don't really care what happened between point EI and point EF, because as long as there's conservation of energy, we can know that they're equal. This makes our job a lot easier, because we don't really care how it got from EI to EF. It could have been a very simple trajectory, or a very complicated one that's hard to graph. What we really care about is those 2 points. So then we set the two equal, and when we subtract things out, what we'll usually get is either our answer directly or some sort of data point or value that will solve the problem for us. To remind you what this looks like, EI breaks down into the initial kinetic energy and initial potential energy, which is 1/2 mvi squared, the initial velocity, plus ui, the initial potential energy. And EF breaks down the same way, and it's equal to 1/2 mvf squared, the final velocity, plus uf, whatever the potential energy may be there. So let's look at an example like this where we have conservation of energy, and then we'll see what happens if we don't have conservation of energy.